Today we will talk about OpenEXR audit that we did back in January this year. And without further ado, let's deep dive. And this will be our today's agenda. First of all, we will introduce the OpenEXR project. Then we will take a look at our fuzzing campaign that we conducted to spot some quick bugs. Then we will perform some root cause analysis for such bug to understand if they are vulnerabilities in the project. And then we will run the extra mile, turning potential impact for those vulnerability into real world actual impact. So let's start with the context. What is OpenEXR? OpenEXR is an open source file format and specification used mainly in the VFX, animation and motion picture industries. And it was originally developed by Industrial Light and Magic company. It was released then as open source. And from then, many other companies in the field contributed to it. For example, Walt Disney Animation, DreamWorks, Pixar, and many more. It is also used in Apple Vision Pro devices. The OpenEXR library is mainly composed of two components, OpenEXR, that is written in C++, and OpenEXR core that is instead written in C. And both of them have the parsing logic to read and write and parse EXR files. And as you may know, those two are memory unsafe languages, and they could be problematic if used incorrectly because they could lead to memory corruption bug and vulnerabilities and so on. The OpenEXR format specification is also really complete and feature-rich. It supports many compression algorithms. It supports many different ways to store the component of an image of a scene, and this all adds up to a big attack surface that attackers can attack. And this is where Shielder comes into play. We were contacted by OSTIF to perform a preliminary security review and threat model analysis of the OpenEXR reference implementation. And what does preliminary security review means? Basically, we had only a few days to get a general picture of the security posture of the problem of the project, understand if there are low-hanging bugs that could have been fixed, and to later consider if a deeper security audit is maybe needed. So since we only have a few days to perform this gig, and since we are talking about memory unsafe languages, we decided to start a fuzzing campaign. And before starting our fuzzing campaign, we tried to build a fuzzing corpus that is a set of test cases to run our fuzzer. And we gathered real-world images from various sources, for example, Academy Software Foundation itself, NVIDIA, Blender, also image sharing services that allowed users to upload EXR files. And so we built our set of starting images. Then from there, we looked at the current state of EXR fuzzing, and here, hats off to the maintainers because the fuzzers are really mature and well documented. However, we noticed that only 25% of the code is actually covered by OSS fuzz. So this we try to understand what is the reason, because the fuzzers are really mature. The project is like since 2020 on OSS fuzzed, so the coverage seemed a little bit on the low side. So we started looking at the entry point for the fuzzer, that is this EXR check binary that basically read EXR files with all feature enabled, all compression algorithm enabled, and validates the content of the image and check the correct behavior of the software. If there is an error or if the image is corrupted, it will trigger an exception, or otherwise it will go on processing it. And we noticed these two flags, -m and -p, that allow to avoid excessive memory allocation or excessive time spent on a file. And these also say some files will not be fully checked. So we looked at those flags, and here is an excerpt from the source code. On the top, you can see that those two flags, reduce memory and reduce time, are passed to the fuzzer entry point, and those two flags are always set to true. And if we look at the line number, on the side of them, we have the number of execution that the fuzzer executed this line. And on the bottom of the source code that we are showing, there is a second branch of the if case that is never reached. Basically, this part of the code is never fuzzed because the reduce memory and reduce time flag are always set to true. And for this reason, we are missing out on a lot of test cases that could take some time, or that could be big images that take memory to process. But in this case, those images, those test cases will be discarded instead and will not be used for fuzzing. And so why those boundaries, those limits are there? Because OSS fuzz itself has this kind of limits. Why such limits are there in the first place? It's to avoid abuses of the free OSS fuzz infrastructure. Basically, OSS fuzz is free, sponsored by Google. You can fuzz there and run your fuzzer, but you cannot abuse it. So if a fuzzer runs more than 25 seconds, its execution is stopped, is hanged, and a timeout will be reported instead. But for our cases, this is not beneficial. This is not ideal, because OpenEXR images in the real world are really huge by design. So this is a blocker. We are missing out on a lot of coverage for our fuzzer. So we rented a server on Hetzner with enough gigabyte of RAM to process our big images, and we set those flag, reduce memory and reduce time, to false, to not prevent us any execution. And after a couple of hours, AFL started reporting some crashes. Here you can see 47 crashes, but those are not really unique. There could be duplicates in there. And also, not all crashes are actual vulnerabilities. Some could be maybe assertion in the code that like triggers a crash, but that's not like really a vulnerability that we care about. And so we took all our crashes and we ran them through Kazur. Kazur is a tool with some kind of heuristic that will detect if those crashes are exploitable and what type of primitives they grant us. And here we can see, for example, these crashes that grant us a keep buffer overflow in write mode. This is a really nice primitive, and it is indeed flagged as exploitable. And here are the vulnerabilities that we that we reported to the maintainers of the project, and really many thanks to them. They helped understand the real impact of these vulnerabilities after some conversation and discussion. And the first two are denial of service vulnerability with a low severity impact. Basically, if you open an EXR file that triggered that vulnerability, the program will crash, will simply crash, so denial of service. The third vulnerability is an out-of-bound heap read. So it could be used to leak information from the heap, so granting an info leak primitive. And instead, the last one is the one we were looking before. It's a heap-based buffer overflow in write. And in some scenarios, this could also possibly result in arbitrary code execution, so granting attacker code execution in the context of a software. So now that we have reported and look at the vulnerabilities, I will pass the mic to Pietro that will do the extra mile.
Thank you, Davide. So as Davide mentioned, one of those vulnerabilities that we identified looks particularly nice and interesting to us. But how nice is it really? So in order to understand the vulnerability, to spend more time with the vulnerability, we need to do root cause analysis. We need to go like upstream in the chain and understand what's the reason why the vulnerability exists in the first place. We start our analysis from this function, which is in the call of in the chain of functions that reach the bug. It's a function that, as you can see, we don't really need to go into the internals here, but what you can see is that we have those 3 variables in the signature. We're taking count bytes from the source, and we're processing those bytes somehow, and then the result of that processing is going into out. We attach pwned, which is an extension of the famous GNU debugger, but meant for security research and exploit development. And we start analyzing what are these out and source variables. By looking at this debugger, we see indeed that those 2 variables belong in the heap. So as expected, they're in the heap. But what can we gather more from this? Where's the problem? So we resort to this malloc usable size utility, which tells us how much space a given heap variable can fit. In this case, see that we're first printing the usable size of the destination buffer, and it's 264. And then we print the count, which is more than 7,000. This is kind of weird. Like, we're trying to fit more than 7,000 bytes into 200 bytes. This looks like it could be the source. This looks like it could have something to do with our crash, with the heap overflow crash. This is not going to work. Let's look at the backtrace more deeper, and let's see if we can go upstream and understand where this problem originates. In the backtrace, there's one particular function that seems interesting. It's this EXR uncompressed chunk. In order to understand this function, we really need to understand a bit about OpenEXR images that, as mentioned, is a very complex and feature-rich format. So we just really scratched the surface. But in OpenEXR images, there's an important distinction between flat and deep images. Flat images are images where for each channel, each pixel has a single value. Imagine an RGB image. So we will have one value for each pixel, one value for R, one value for G, one value for B. Deep images instead are meant to represent 3-dimensional images. So for each channel, each pixel can have an unlimited number of values, and each value will be associated to a certain depth of distance from the viewer. This is important because given how feature-rich this all part is, we need some flexibility in the OpenEXR format. In fact, this flexibility exists. So OpenEXR stores blocks of pixel data in what it calls chunks. The chunks contain the pixel data, and the chunks can be compressed to save space. But since we cannot know beforehand how many in big images, how many bytes, how many pixels we have, how many samples we have for each pixel. We need some, we need to have some information in the header. And in the header of each chunk, we have two pieces of important information. We have the size of the compressed data, and we have the size of the uncompressed data. How does it look like in the code? We have something like this. We know that when the chunk, when the parsing code is parsing the chunk header, at some point it will store this packed size and unpacked size, and it's taking these values from the header. And this can originate some security problems. In this case, imagine that we have a situation like this. We have some pixel data. The pixel data is going to be packed and compressed. And imagine that we then have resulting chunks with a given packed size and unpacked size. So far, so good. But what if, as an attacker, we just change the unpacked size in the value in the chunk header? So what will happen is exactly what we've seen in the debugger. We will try to get the decompressed data fitting into a smaller buffer. In this case, for instance, we originally had 180 bytes, and we will try to fit those 180 bytes into 20 bytes of uncompressed data buffer. This is what we ended up understanding about the vulnerability, and it is also what we wrote in the CV description. In fact, you see the forged chunk header. And since we have a heap overflow, the standard formula is to assign a high or critical severity, and also we use that formula there could potentially result in code execution in the process. Okay, that's over. As security researchers, we happy we made the world a little bit more secure, right? Not really. We have an extra mile company culture, we would say. So we have some security research time. And a couple of months ago, I decided to spend some of this research time to investigate more about this vulnerability, because it seemed interesting, the whole project and the vulnerability and the software that is using this library. So it feels that could be a big impact. So what if we don't like that potentially word there? What if we want to demonstrate that potentially word there can shrink and demonstrate that the vulnerability can actually be used for remote code execution? So let's do some exploit development, and let's really understand the power of this vulnerability. In order to study this buffer overflow from an exploitation perspective, we need to shift the mindset. Here we are testing a library, but in order to write an exploit, we need to see we need a place where the library is used, which means a specific operating system, a specific program. So we build a lab. And this lab is a Linux operating system. We're using the version of OpenEXR that we tested, and we wrote a reference binary. It's a bit like a capture the flag binary, if you know the concept. So we basically just have a binary exposed on the network that accepts an EXR file. It checks if the EXR file is okay, and it returns a string okay if the file is good, or bad if the file is not good. There's a peculiarity though. There is a hidden win function in the binary, and it's a very simple function. It just checks if there's a connected client, and if so, it sends a flag to the client. Now, the cool thing is this win function, of course, is never explicitly called in the EXR server binary. So the goal of this research is to demonstrate that we can leverage the heap overflow to redirect the code execution to this win function. Let's start by understanding how much control we have over the bug. Okay, we have a heap overflow, but how much data can we really control? Do we have bad bytes? Can we use null bytes? Do we have weird constraints? The first question is easily answered. Pixels can be represented by different kind of variables, and in particular, they can be even represented by unsigned integers. So in terms of what data we can use as our payload, we're quite, we have a large degree of freedom, because we have proper unsigned integers, so no bad bytes. What about the weird constraint? Well, I don't want to go too much into the internals, but I think it's a really interesting mention here that we have here the code that is taking care of actually decompressing the buffer. Now, because of this edge case, where we are making the uncompressed size smaller than the compressed size, and you can see that is a bit weird, because usually when we compress things, we expect the decompression to result in larger data. Because of this edge case, we end up with two particular constraints. And these constraints are basically telling us that the decompressed data cannot be bigger than the compressed data, and the decompressed data cannot be smaller than the compressed data. And this is just because of how the checks in the internals work. I mean, vulnerabilities are cool and everything, but even just when you seem to have something very powerful like a heap overflow, there will be things in the code that will try to create checks. So it's not as easy as it sounds. So because of this, we have this particular constraint, and the only way we can have these two constraints satisfied, by that the unpacked data cannot be bigger than the packed data and the unpacked data cannot be smaller than the packed data, is that we need to have a compressed payload in the chunk that when decompressed has the same size of decompressed payload. If you think about it, I know that this part is kind of complex, so it's not really important to fixate on it, but I think it's a really interesting finding here. Because as you can expect, when you compress something, you expect this, you expect the data to shrink. You expect that the compression shrinks the data. However, it's not always the case. In fact, compression leverages patterns in the data. What kind of data doesn't have patterns that we can use to compress? It's random data. So what happens if you try to take a random data buffer and if you try to compress it, you will actually end up in a compressed data that is bigger than the original data. And this is because the original data was not compressed at all, because it doesn't have patterns that can be used. And there will also be a overhead introduced by the compression algorithm. And this is exactly the technique that I've leveraged to gain that situation where the compressed data size and the decompressed data size match. Basically, it's by combining a big part of random data that cannot be efficiently compressed with a small part of controlled data. By coupling this and by just running the script a couple times, we get a payload that, in fact, it has that satisfies that constraint. And then just coded a simple utility that reuses OpenEXR, but it's slightly patched so that we can build OpenEXR files, but in a controlled chunk, we can replace the data and put our compressed payload and make the unpacked size in the chunk header small at will. And this is how we can control a malicious OpenEXR file. So we do have a good degree of control. However, now that we can control a heap overflow, it's really useless unless we have a target to actually write. We need a way to transform this overflow into a remote code execution. Now, usually, capture the flag, like extra skilled pawners, will try to exploit heap internals. They will try to exploit heap metadata, use techniques like house of force, house of spirit, and that kind of things. However, that would be a bit complex in this case for many reasons, and also it will depend on the version of the libc that is running on the target. It will be very unreliable. There's another method that we can use though. We have in the heap a lot of OpenEXR related objects, a lot of proprietary objects that belong to the library. Can we try to reuse those objects? Can we find something that we can overwrite in the OpenEXR object store in the heap that can give us a remote code execution primitive? And what this questions really means is, can we find any OpenEXR object that is in the heap and that has a function pointer that we can overwrite? to gain remote code execution? We do this kind of research, read, ChatGPT, so on and so forth, and we end up with something. In the EXR context, one of the important objects stored in the heap that represent the context is the attribute lists. EXR attributes are basically metadata describing the EXR file. There are required metadata and optional metadata, things like the display window size, the compression type, or things like the author name or the program that created the EXR file. What these EXR attributes look like is that they have a common header with things like the name, the type, and then they have an inner pointer that points to another object that is the actual specific attribute. And we have many kinds of attributes. So for instance, we have the string attribute that has a length and a string pointer to manage the string. There's one particular kind of objects that is really the kind of attributes that is really interesting for us. And it is interesting because among its fields, it has a function pointer property stored in the object. And the reason it has that function pointer is that because when we destroy the EXR context, so when we, for example, the EXR file goes out of scope in the C++ code, we need a way to deconstruct these attributes. And this kind of opaque attribute gives the programmer the freedom to specify their own custom function to destroy the wrapped data of the attribute. And what if we can leverage this for remote code execution? So the goal works like this. We have the target chunk that we can overflow. We have an existing attribute living in the heap. We use the overflow to replace the existing attribute with a fake opaque attribute. And we put the destroy unpack function pointer to point to the win function that we want to call. Then we just need to wait for the EXR context to be destroyed, and we're going to call the win function. There are some issues that we need to solve. We have an ideal heap layout that I showed before, where we want the target chunk to be before the attribute because we need to overwrite it. But really, we will usually have the opposite way around. In fact, since attributes are parsed before pixels, probably the attributes will be placed before the chunks of pixel data. Therefore, we cannot overflow with the existing attribute with the chunk. First issue. Second issue, even if we can magically get this ideal heap layout, what about the data that is in between? We cannot just hope to overwrite random stuff in the heap just to get to the existing attribute, because probably before the EXR context is actually deconstructed and our remote code execution primitive runs, we will probably crash the program because of a million other reasons. This is the second problem. The solution to both these problems is called heap feng shui. We cast this spell. Heap feng shui is basically a technique of exploit development where we carefully select sizes and order of allocations so that we can predict and control the heap layout. It works like this in this case. We have this EXR server, and we can just send EXR files, more than one if we want, because it's exposed as a service. So we'll just accept files and then close the connection and then accept new files and so on. So we will first send a good EXR that doesn't have any tampered unpacked size for the overflow. It will only have two custom attributes with very specific sizes. In this case, one attribute will have 160 of size and the other attribute will have 176. When the EXR server receives this file, it will allocate two heap chunks to store these attributes, and they will be contiguous because the attributes are parsed together. Then the EXR server finishes parsing that EXR file. The heap will free those chunks. Now, you should know, maybe you don't know, but probably you know if you have decoded a bit you developed in C and C++. The heap, when it allocates data to store objects, when that data is deallocated, the heap will basically put that area space in a free state. This way, if we then request as a program we try to allocate that exact size again. The heap will try to reuse 3 chunks instead of allocating new ones. And this is, of course, for optimization purposes. We can leverage this for heap feng shui. We will send a new file, and this time this file is evil and it has deep overflow. And it works like this. It has an attribute that has the size of the second space. So it's 176. And it has a chunk that has the unpacked size of the first variable. This way, when the XR server will parse this file, it will reuse the 3 chunks exactly as we want. And if you remind what we wanted, this is exactly our ideal layout. We now have the chunk that overflows and the target attribute that we want to overflow, right? They are adjacent and they're right next to each other. We'll now try to run the exploit and see what happens. You see in the run of the exploit that there are some debugging printing statements that I have added. When the first file, the good file, is parsed, we see that we have these 2 addresses that are used for the attribute allocation. Then we send the evil XR file. And you see that the attribute is indeed reusing the address of the second attribute here. And the target chunk that we are overflowing is indeed reusing the first attribute space. So we confirm that the heap feng shui worked as expected. Let me now very quickly, can I delete it from here? Slide media control, yeah. Let's now see the exploit in action. I will just run, it's just running the EXR server on a given port, 31337. And then we are launching the exploit first with a good EXR file so that we prepare the heap. We do the heap feng shui, and then we send the evil EXR file. As you can see, the EXR server crashed, but before crashing, it is printing the win message and the client received the flag, showing that the remote code execution happened as expected. Now, before closing this research, it's important to mention that this I didn't go too deep into the specific exploitation, like how to calculate the addresses and stuff. However, it's important to know that in order to perform this attack, we need a leak, or we need the binary to be compiled with no pi, no position independent executable. Now, how unreasonable this precondition is really? Let's see. Let's say that we take one of the most famous programs that use OpenEXR under the curtains. Let's say that we attach a debugger to this program called Blender. Let's say that we supply the deep EXR file and we confirm that Blender is indeed going in segmentation fault, so it's impacted by the same heap overflow vulnerability. And then let's say that by checking the security mitigations applied to the binary that is released in the Blender Linux build, we see that it's compiled with no pi. So I guess that as a precondition is not entirely unreasonable. Closing this part of the presentation of the meetup, I think that the main take of this research is that sometimes it's hard to draw the line between memory corruptions that just crash the program and memory corruptions that are actually security problems. But in general, we really need to understand that maybe assuming the worst is a good thing for the threat model. The reason we assume this is that because if we, with our small research time and relatively small will to do all of this extra mile, if we could do this, threat actors which have more time, more resources, and more drive to do this, they can definitely do this and much, much worse. We should, when fuzzing, it's important to consider the limitations of even powerful and extra cool fuzzers like OSS fuzz. I think that the really important part to conclude here, we always say when speaking of software, that we stand upon the shoulder of giants. Well, projects like OpenEXR are exactly these giants. And if we want to stay high in the sky, we need to protect our giants. So it's extremely important that OSTIP is fighting this battle. We are thankful for the OpenEXR developers that quickly triaged and helped us understanding the issues and fixing them. And we're happy to be part of this battle against the open source insecurity. Thank you. Always remember that the full audit report is available basically lots of places, either by looking at the Discord code or OSTIP website or Shielder GitHub repository. And this is a wrap. Thank you. Sorry if we went a bit over time, and hopefully you have lots of questions and this was interesting for you.